Welcome. In today's video, we're going to derive an expression for the mean and variance of the normal distribution. To begin with, let us first remind ourselves of the probability density function. So recall if x has a normal distribution with parameters mu and sigma squared, then the probability density function, or the PDF of x, is given by the following. F subscript x of x is equal to 1 over sigma square root 2 pi exp of negative a half x minus mu over sigma all squared. And this is applicable for the range x, or the domain x is an element of the real numbers. Let us now look at how to evaluate expectation. So, for a normal random variable, x is a continuous distribution, and therefore we're going to use the continuous definition of expectation, which is, of course, the following. The expected value of x is the integral across x in the support of x, or the sample space of x multiplied by fx of x dx. Now, in this particular example here, our support that we are interested in, or our x is an element of x is an element of omega x, is the real number line. So our terminals need to go from negative infinity to infinity. We've still got our x times, and now what I will do here is I will copy across the definition of the PDF that I just put across here. And then, of course, we're integrating that PDF with respect to x. It is at this point that I will pause and notice that this is a somewhat difficult integral to evaluate, but I do notice one thing, and one thing that I'm hoping will help us in the long run. See here, I have an exponential, I have an exponential function of a power, of specifically a power which has x squared as my power. I also have an x here. So theoretically, there might be a way in which we have the derivative down the front here and a power of x squared inside the exponential. So maybe somewhere down the line, we're going to be able to integrate this quite easily. For now, however, what I will do is I'm actually going to define I'm going to perform U substitution. And by performing U substitution, we will be able to hopefully integrate this expression. So, the logical choice here might be the whole of the U that we see here, or might be the whole of the x minus mu over sigma all squared. But for the purposes of this, I'm actually going to just define it as the inner circle, or the inner linear function. One, because it's easier to work with linear functions when differentiating, but also when we do eventually substitute this through, I'm going to get a half something squared, or a half variable squared, and there are some standard integrals that we might know of when dealing with that. So without further ado, let's have a look at what we get. So let y is equal to x minus mu on sigma. So what do we get from this? Well, the first thing we get is we can get a rearranging for x. So that tells us that x is equal to mu plus sigma y. We also get told that dy on dx is therefore equal to, well, in this particular instance, we have a power here, sigma on, we have a linear function in x, where 1 on sigma is the constant out the front. So the derivative of something times x is just the something, which is the 1 on sigma. And therefore, if we rearrange this equation, what we will get in terms of dx is dx can be rewritten as sigma dy. The last thing to point out, of course, when we perform substitution is we need to work out what the terminals will be under the new domain. And so we can do that very quickly. We note that when x is equal to negative infinity, if we have a look at this expression here, when x is equal to negative infinity in this particular expression, well, y will also equal negative infinity. Negative infinity, because when we scale it, when we subtract mu and even scale it by sigma, that's not going to do much to infinity, negative infinity. It'll just keep it at negative infinity. And of course, by the same logic, when x is equal to infinity, y will equal to infinity. Again, because subtracting a constant term and dividing by a constant term will still end up with infinity, because infinity, of course, is so big. Now that we have performed our sort of substitution here, let's rewrite the integral. So the expected value of x is still negative infinity to infinity. The x, or the x value here, we actually recalculated in this part here. So we can rewrite that as mu plus sigma y, close the brackets. We've still got our 1 on sigma square root 2 pi from the expression above. And then, of course, this expression here will simply collapse to, we just need to replace this component here with our y. So that becomes exp of negative a half y squared. And finally, our dx expression here, we came up with an expression, is simply sigma dy. So we can write that now here. Sigma dy. So far, looking good. So one thing I'm going to notice, the first thing is that the sigma here down the bottom in the numerator, in the denominator, will cancel here with the sigma at the top. So without further ado, I'll just do a little bit more simplification. That's still negative infinity to infinity of mu plus sigma y all over times 1 on square root 2 pi exp of negative a half y squared dy, which is all good. Now what we're going to do is I'm going to separate this product here into two terms. The first term will be the mu over 2 pi, or square root 2 pi, and the second term will be the sigma y over square root 2 pi times the exponential. So let's do that here. Becomes negative infinity to infinity of mu over square root 2 pi exp of negative a half y squared, and then plus sigma y over square root 2 pi exp of negative a half y squared dy, and we're integrating that all. Now, by properties of integration, we know that when we integrate two terms, or when we integrate the sum, I should say, the sum of two terms, that is the same as integrating or taking the sum of the respective integrals. So we can actually split out that sum here. 2 pi exp of negative a half y squared dy. And then, of course, we're still integrating with respect to y, sum of negative infinity to infinity of sigma y on square root 2 pi exp of negative a half y squared dy. So far, so good. Then, for the first part here, I will acknowledge that this mu on sigma square root 2 pi is independent of our integral, or what we're integrating with respect to. So I can actually take that out as a constant. So what I will do here is mu on square root 2 pi integral of negative infinity to infinity of exp of a half y squared dy plus, and in a similar effort, what I can do here is acknowledge that the sigma and the square root 2 pi are also independent of what we are integrating with respect to, so they can come out the front. So we can say, we can take that out as a constant at the front of the integral, negative infinity to infinity of y exp of negative a half y squared dy. So far, so good. Now, the first term in this sequence is in fact a well-known integral. The integral of negative infinity to infinity of the exponential of a negative a half y squared, by definition, so I'm going to write the first term here, square root 2 pi, is the square root of 2 pi. That is a well-known integral. We will cover why this integral is the case in a separate video, but for now we will take this fact as given. The second term here, I'm going to still rewrite for now. Square root of 2 pi, sum negative infinity to infinity of y exp of negative a half y squared dy. So far, so good. And then, of course, if we wanted to simplify the first term, we just know that that's mu plus, of course, because the square root 2 pi and the square root 2 pi cancel. And then I'm still left with the term that I had before, negative infinity to infinity of y exp of negative a half y squared dy. Now, what I will do here is I want us to first recognize that this function in here is what we call an odd function. And an odd function simply means this. It means that, by definition, just as a side, g of an odd function, by definition, as an aside, odd function is if you have a function and you take the negative of x, that is the same as taking negative f of x. That is what we mean by an odd function. And I'll prove it to you that this function here is an odd function. Quite simply, let g of y equal y exp of negative a half y squared. So that would mean that g of negative y would be, let's substitute negative y into this function. We would get negative y as the first term instead of y. And then we would get exp of negative a half and then negative y again instead of y, and then we'd have to square it. And this is negative y exp of negative a half y squared. Again, why does it simplify to y squared? Well, because when you take square of a negative number, you get back to a positive number here. And then what do you notice about this expression here? The y exp negative a half y squared, that first, or the second half of that expression is just g of y, but we've got a negative in front of it, so that is negative g of y. And so here what I'm going back to that definition of an odd function, when you take f of negative x, you get negative f of x. Here we've taken g of negative y and we get negative g of y. Tells you, therefore, g of y is an odd function. Now, why was that even useful, or why did we bother with defining an odd function? Well, there is an important property of odd functions, and this important property is as follows. If f of x is an odd function, then the following is true. The integral of negative a to a of f of x dx is simply 0. And the reason for why that is the case, as a little bit of a visual explanation here, is if I were to draw you just a generic odd function for the time being, and let's say it looked like this on this side, x, y, and then because it's an odd function, it would be symmetrical the other way around. And if I were to say, here is my negative a, and here, I guess, is my positive a, and I were to integrate with respect to x along this interval, I would be integrating this area here, and then I would be integrating this area here. And basically what we'd notice is that by virtue of the fact that it's symmetrical, except negative but symmetrical, the two areas here would in fact cancel each other out when integrating across the entirety of the domain. And therefore, by that same logic, the integral must be 0. So now that we've established that for an odd function, the integral from a symmetric point, or an integral from negative a to a of f of x dx is 0. Now going back to the original question about expectation here, we notice that we're going from negative infinity to infinity, which is technically the same range, except the negative range. This whole expression here must be 0. And therefore, our expectation of x is equal to mu plus sigma on square root 2 pi times simply 0, which is equal to mu. And so that is the definition, or that's how we can calculate the expected value of x. And of course, we expected this because a normal distribution by definition is defined with respect to the parameter mu, which is meant to be its mean. So now let's take a look at the variance of the normal distribution. Have a look. So again, to compute the variance of the normal distribution, we will first have to derive an expression for the expected value of the second moment. So the expected value of the second moment, by definition, is the integral from negative infinity to infinity of x squared fx of x dx, which in this particular instance is negative infinity to infinity of x squared multiplied by 1 on square root sigma 2 pi exp of negative half x minus mu on sigma squared dx. Similar to before, what we will do is we will do a similar substitution. We will say let y equal x minus mu on sigma, and then it follows that, well, let's again derive the same sort of expressions. X has to be equal to mu plus sigma y by rearranging the linear equation. Dy on dx, as we discussed before, was 1 on sigma, which in this particular case means that dy, or dx, I should say, dx is equal to sigma dy. And of course, we know when x is equal to negative infinity, y is equal to infinity, and when x equals positive infinity, negative infinity above, y is equal to infinity here, as we established before. So that means that our integral x squared follows the following. So it would become negative infinity to infinity of x squared, which we now rewrite as mu plus sigma y all squared, times 1 on sigma square root 2 pi exp of negative a half y squared sigma dy. And that's just substituting in our values of y and x, or values of y or values of x in terms of y from above. From here, the first thing I'll notice is that the sigma and the sigma here cancel out. And then the second part to evaluate here is to, I suppose the next logical step might be to expand the expression here, or a polynomial expression. Without further ado, let's do that. So that gives us negative infinity to infinity of mu squared plus 2 mu sigma y plus sigma squared y squared times 1 on square root 2 pi exp of negative a half y squared, and integrate that with respect to y. And in a similar fashion to before, what I will be doing is I'm going to push through or expand the product here and evaluate the product of these terms as they fall through. So let's do that here. Negative infinity to infinity of the first term here is the mu squared and then the half over square root 2 pi exp yada yada yada. So we've got mu squared on square root 2 pi exp of negative a half y squared. Second term here that we've already evaluated, needs to be the 2 mu sigma y times the second expression. That becomes 2 mu sigma y on square root 2 pi exp of negative a half y squared. And then finally, the final expression here that we shall evaluate is the sigma squared y squared times our expression. So we've got to have plus sigma squared y squared on square root 2 pi exp of negative a half y squared, and then of course we're integrating that with respect to y. Now, in a similar fashion to before, what we can do is the fact that the integral, we have the integral of a sum of functions, is the same as taking the integral of the respective functions and then summing those integrals together. So we can rewrite that as negative infinity to infinity of mu squared over square root 2 pi exp negative a half y squared dy plus the integral of negative infinity to infinity of 2 mu sigma y on square root 2 pi exp of negative a half y squared dy. And then finally, the final integral, negative infinity to infinity of sigma squared y squared over square root 2 pi exp of negative a half y squared dy. So far, so good. And then finally, we can evaluate the next step, I guess, in this expression is to take out all the factors that are independent of our integral, or dy. So in this first expression here, the mu squared and the square root 2 pi are independent of our what we are integrating with respect to. So we can take those constants out the front. Exp of negative a half y squared dy plus, in the second expression here, the y and the exp of negative a half y squared are dependent on what we are integrating with respect to, but the 2 mu sigma square root 2 pi are not. So that can be rewritten as 2 mu sigma over square root 2 pi times the integral of negative infinity to infinity of y exp of negative a half y squared dy. And then finally, our last expression here for the day is our square root, or sigma squared, and our square root 2 pi are independent of what we're integrating with respect to. So we can take them out the front of the integral here, negative infinity to infinity of y squared exp negative a half y squared dy. So far, so good. This first expression, now going back to the front here, we evaluated this expression or this integral before, or I gave you the expression itself, mu squared square root 2 pi. By definition, this is a known integral and it evaluates to the square root of 2 pi. This second expression here, we also evaluated previously above, and we noted that it was an odd function and therefore integrated to 0 when evaluated. So this second half of the expression will simply be 2 mu sigma on square root 2 pi times 0. And this final expression here that we have, well, this might require a little bit of work. So I'm going to leave that as is for now. Square root negative infinity to infinity of y squared exp negative a half y squared dy. After some simplification, the square root 2 pi and the square root 2 pi cancel here. leaving us with simply mu squared, and then this whole expression, the second expression, just disappears because it's being multiplied by 0. And of course, we have our final expression here, which we will still need to evaluate. Y squared exp negative a half y squared dy. From this point onwards, what we will need to do now is do another substitution. And perhaps a logical substitution that might follow here is to remove the 2y or the half y squared. Because if we label it as the half y squared as our substitution, then we'll end up with an exponential of negative variable. And typically dealing with that is easier to deal with than other integrals necessarily. So without further ado, let us define z is equal to negative a half y squared. Sorry, apologies. Just a half y squared for now. This implies a few things. The first thing it implies is that that y is equal to, if we rearrange the equation, the square root of 2z. And you might be saying it's going to be plus minus the square root of 2z. And you would be right. And equally, what you could say is that dz on dy, by definition, would be equal to simply y, which is plus minus the square root of 2z, which implies dy, if we were to rearrange our equation, would be dz over square root 2z plus minus. Now, here's the thing. I don't want to deal with plus minuses. Plus minuses are a little bit complicated. So the second concept here that I'm going to introduce is actually going to be what we call an even function. And an even function, on the side here, and an even function is defined as follows. If you take f of negative x, you get back to x. So focusing our attention on the function in here, I'm going to prove to you that this is in fact an even function. So let h of y equal y squared exp of negative a half y squared. Then h of negative y would be, well, now wherever we see a y in this expression, we need to substitute a negative y. So for the first term, it's negative y all squared, exp of negative a half, again, negative y all squared. After some simplification, again, here we've got a negative y all squared. When you take a negative and you square it, you end up back with the positive. So that becomes just simply y squared, exp negative a half. Similar reasoning here, negative y squared or negative y all squared. Negative squared becomes a positive. So we're just left with y squared. And then, of course, hey, what do you recognize? This is by definition what we call h of y. And so it is true, in fact, that this expression here is an even function. Now, here is one of the interesting properties of an even function. So if f of x is an even function, then this can be said, the integral of negative a to a of f of x dx is equal to 2 times the integral of 0 to a of f of x dx. Now, we can also visualize this in a similar way to before that we looked at the odd function. So again, imagine you have an even function that sort of looks like this in the first quadrant. Now, by definition of the fact that it is an even function, then it actually needs to look like the mirror image on the opposite side. And if we went from negative a to a, and we were to integrate this area, you'd notice by the fact that it is a mirror image of itself, and here, of course, is the origin. Because it is a mirror image of itself, the first or the second area here is exactly equal to the first area. And so instead of going across both areas, we can just take a look at the first quadrant area and multiply it by 2. So going back above to this expression here, instead of going from negative infinity to infinity, we can actually say we can just go simply from 0 to infinity and then put a 2 out the front. So that's what we'll do. The expected value of x squared is equal to, I think it was mu squared plus, taking that expression, let's take a copy of it, copy, paste our expression here, but now we're not going from negative infinity, we're going from 0 and we're multiplying by 2. Now we can go back to our expressions for z. And because we're only dealing with the interval from 0 to infinity, I don't need to worry necessarily about the plus minuses. So I'm just going to ignore the plus minuses altogether and just take a look at the positive versions. Because again, we're dealing with that interval from 0 to infinity. So now that we've got our z substitution, we can go back to mu squared plus 2 sigma squared on 2 pi. And yes, the other thing to note is, before I continue, we're going from 0 to infinity for y values. And of course, when y equals 0, z equals 0, and when y equals infinity, z equals infinity, back up here that I forgot to mention. So when we substitute in these terminals here from 0 to infinity, they need to be from 0 to infinity. Now our expression for y squared, well, what did we say our y was equal to? We said it was equal to the square root of 2z. So let's replace that as the square root of 2z all squared. Then we've got exp of negative. We said what this was before. This was just negative z. And our dy, or our expression for dy, if we go back up here, we said dy was dz on the square root of 2z. So that becomes dz on the square root of 2z. Whew. Now, what I will firstly notice here is that this square root 2z will cancel with one of the square root 2z's here. So that just simply leaves us with mu squared plus 2 sigma squared on square root 2 pi integral 0 to infinity of square root 2 square root z exp of negative z dz. The other thing to note is, now that we've evaluated this integral, is that the square root 2 here will cancel with the square root 2 in the denominator here. So this can now be re-expressed as mu squared plus 2 sigma squared all over square root 2 pi and 0 to infinity. And the last part to note, square root z, I'm going to rewrite as z to the half exp of negative z. Or actually, in simpler terms, I can rewrite this as e to the negative z dz. Now, from here, we actually might need to recognize a very important function. And it is here where I will introduce to you the gamma function, or hopefully a function that we have come across before in your studies. And the gamma function, which is defined to be the following. Gamma of t is equal to the integral of 0 to infinity of z to the t minus 1 e to the negative z dz. This is by definition the gamma function. And it has a number of properties. For example, one of the properties is that for t is an element of the natural numbers, this is simply equal to t minus 1 factorial. And I should say for t an element of the natural numbers. Now this is good because would you look at what we have here? This expression up the top is looking awfully like the gamma function. In fact, it looks exactly like the gamma function, except instead of a t minus 1, I have a half. So if, for example, I was to rewrite our expression above mu squared plus 2 sigma squared on square root pi of 0 to infinity, instead of z to the half, I was to rewrite that as z to the 3 on 2 minus 1 e to the negative z dz. We now have an expression that looks exactly like the gamma function. And then from here, we can therefore write is equal to mu squared plus 2 sigma squared on square root 2 pi gamma of 3 on 2, by definition of what the gamma function is up above. Now, here is an important property of the gamma function. There are two properties that are really important. Property number 1 is this. Gamma of t plus 1 is equal to t times gamma of t. That is important property number 1. Important property number 2 that we are going to utilize is that gamma of a half is equal to square root pi. These two properties in combined will allow us to evaluate the integral above. We will cover the gamma function and its properties in some detail in another video, but for now, consider these as given results. From here, this allows us to say that the expected value of x squared is equal to mu squared plus 2 sigma squared on square root 2 pi. Here comes the first use of the property. Apologies here. The gamma 3 on 2, by virtue of the first property, could be rewritten as gamma a half plus 1, which by the first property 2 sigma squared square root pi. Sorry, I think I made a mistake here. It's not square root 2 pi, it's just simply square root pi up above. So let me correct that everywhere, just down the bottom here. Square root pi. By virtue of the first property that we discussed before, we've got a half plus 1. So t plus 1 got a t value of a half. So therefore, that must be equal to a half gamma a half. And by virtue of the second property that I've stated above, times a half times square root pi of the second property discussed above. And then after some cancellation, we can cancel this 2 with the denominator of the 2 here. We can cancel the square root pi with the square root pi here. And therefore, we are left with mu squared plus sigma squared as the expected value of x squared. And finally, that allows us to evaluate the variance of x. By definition, that is the expected value of x squared minus the expected value of x all squared, which is equal to mu squared plus sigma squared minus mu all squared. As we said, the expected value of x was mu. And then the mu squared here cancels the mu squared here, and we are left with sigma squared. And by the same, for completion, we'll take the standard deviation of x, which by definition is the various square root of the variance, which is the square root of sigma squared, which is just sigma. And there you have it, ladies and gentlemen. What we have done here is we have evaluated an expression for the mean and variance of the normal distribution. We have utilized properties of odd functions. We have utilized properties of even functions. And we have also utilized properties of what we call the gamma function. And the gamma function, of course, had these two very important, one a reciprocal property and two sort of a starting condition property, I would call it, where we know that gamma of a half is the square root of pi. I hope this video was useful. Hope to see you in the next one.